available, but unless you have a 504, like some kind of education plan that says you need filled out notes, I'm not going to give them to you until after the class is over, just because I want you to pay attention. Is that fair? Does that make sense? Okay. So today we're talking about exponential modeling. We've been doing exponential modeling. We know that we can do exponential growth and decay, and we know that we can do percent of change, right? Compounding, did we do that yesterday? So today we are talking about more, we're going to use more modeling, and then we're going to do the discovery of E, discovery of Euler's number. So if a colony of fruit flies has a population that doubles every 8 hours, if something is doubling, what is my multiplier? 2. Okay, so my multiplier is 2. And what is my beginning value? There were 22. So I started with 22 flies. We know that our rate, our multiplier is 2. And we're actually going to write this as, y equals a times b to the power of x. So our initial value is 22. Our multiplier doubling is 2. And how often does that double? It doubles every 8 hours. And we're writing that D, so we're going to use the variable D as our power. Okay. So if H represents the number of hours, this is page 5, okay? If H represents the number of hours since the population was originally at 22, what is that equation that relates H to D? What is the equation that relates H to D? So I made a table of values. So let's see. When H is 8, how many times do I double? Once. My power, my exponent, my doubling exponent is 1, right? We're doing this every 8 hours. So when H is 16, how many times have what's the power on that? 2 times, doubles twice. When H is 24, what's my exponent going to be? 3. Okay, does that make sense? Yes or no? Okay, so we know that it doubles for every hour, for every H value divided by 8. So D, your power, your exponent equals whatever H is divided by 8. When H is 16, 16 divided by 8 is 2. When H is 24, 24 divided by 8 is 3. So that's your power. Does that make sense? Okay, well, we'll keep moving on and see if you catch on. So using your answers from A and B, we're going to write a model for the population of flies. So remember, so we're going to replace D with the expression H divided by 8. Because now we're trying to find the number of hours, like per hour, how many flies there are per hour. We want to know how many flies there are in 5 hours, maybe in 12 hours. Our lives don't run in just an 8-hour increment, right? So our population has an initial value of 22. We know that it doubles, and our exponent is now H divided by 8. Okay. All right. So so it says, by what percent is your population doubling or increasing per hour? Show how you arrived at your answer. So we need to look at just simplifying the exponent piece. 2 times H, 2 to the power of H divided by 8. Well, this is the same thing as saying 2 to the power of 1/8 times h, right? Because when you have two powers, two exponents together, you multiply them, right? So h divided by 8 is the same thing as saying 1/8 of h. So let's figure out what 2 to the 1/8 power is. So that's going to give us our percentage. What is 2 to the 1/8 power? So 2 caret 1 divided by 8. What'd you get? That's what I got 1.0905. 1.0905. So it's asking us for its percentage. And remember that percent growth is 1 plus the rate written as a decimal, right? So if we were to think about this, we added a 1 to this because it's growing. So what is the percent of growth? Well, it's this decimal piece. Our percent of growth is 9.05%. Do you guys remember A? Yesterday we did A equals the principal times 1 plus your rate to the power of whatever, t. Well, we're trying to find out what that growth percent is. We'll just keep practicing. So let's look at this next one. So as long as we're careful when we set up our models, we just have to, what we're really focusing on is paying attention to the unit of time. So radioactive material has a half-life of 35 years, meaning that every 35 years it's cut in half. Exactly. So the multiplier is 1/2 or 0.5. That's what it means by half-life, okay? If a to the 0 represents the original amount present and t represents the number of years it's been decaying, which of the following models represents the amount of A, the radioactive material, that's present after t years? So how often is it cutting itself in half? Like how often does that happen? Every 35 years. So that means that whatever our time is, we have to divide it by 35, right? So every year is going to get divided by 35. I don't think that we should have to make a table for that, right? So you want some variable. I put the number of years over 35. They're using t over 35. But we know that our multiplier is 1/2. Okay, and a to the 0 was the initial amount. So what equation models that? Number 2. So if the correct model from exercise 2 was placed in this function, like y equals a times b to the power of x, that's really what that looks like, says then when would be the value of b, then what would be the value of b accurate to 4 decimal places? So it's saying, hey, now I want you to find b. So we're focused on this multiplier again. So 1/2 times t, or to the power of t divided by 35, that's the same thing as saying 1/2 times, or not times, I'm sorry, I keep saying that. 1/2 raised to the power of 1/35 times t. So I just need you to figure out the power of 1/2 to the 1/35 power. So take 0.5 and raise it to the power of caret function 1 divided by 35. Tell me what we get. 0.9803. Okay, so we know that this is decaying, right? Because it's getting cut in half. So what is the percent? How can we write this as a function. Like, what is this going to look like? It's asking you what b is to 4 decimal places. What came after that 3? Wasn't it a 9 or something, or an 8? Because I got 0.9804. Yeah. Yeah, so that 3.9, that makes us round this up to 0.9804. It was just asking us to find the b value. Asking us to find the b value. So remember that this is 1 minus some value equals the 0.9804. So what is the percent that it's actually decaying? What is its percent of decay? Well, work backwards. Take 1 minus 0.9804. And what do you get? You get 0.0196, which means it's decaying at about 1.96%. 1.96% every time. Can I go on? Yes or no? Okay. So the number of people who know a rumor is a function of days since it started. So talking about gossip, right? So it says, hey, here's the function. This is the number of people that know the rumor. D represents the days. So initially, how many people knew the rumor? Looking at that function, how many people knew the rumor initially? 5. Yeah, my initial value is 5. So the function, the multiplier is 3.8 times the number of days. We want to write a model that represents how fast the rumor has been spreading per hour. Per hour, okay? So let's see. Number of days equals 5 times 3.8 to the power of D. If I want to know the number of hours, how do I change D? How do I change D to represent replication per hour? 1 over 24, yeah. So we're going to rewrite this function. The number of people that know the rumor, and it's now going to be 5 times 3.8, and the number of hours divided by 24. So if I have 24 hours, 24 divided by 24 is 1 day. All we've done is change the way this function looks. Does that make sense? Okay. So what we need to do is we really need to get rid of this fractional exponent. That's what we're trying to do. We're trying to get rid of that fractional exponent. So we need to rewrite this as 3.8 to the power of 1/24 times h. And what do we have to figure out? We have to figure out what 3.8 to the 1/24 power is. So 3.8 raised to the power of 1/24 is I got 1.0572. H is still a power. Do you guys see how we're doing that? Okay. So we know that it's growing or decaying. How do we know? What's happening? Growing or decaying? It's growing. By how much? What percent is this growing per hour? Well, remember that this number in the middle came from 1 plus the rate that was written as a percent, and we turned it into a decimal. So just take the 1 off. Just get rid of the 1 because we added the 1, right? So you have 0.0572. That's the decimal. If I want to turn that into a percentage, I multiply it by 100. So what percent is it decaying at? It's decaying at 5.72% per hour. Or not decaying, sorry, growing at 5.72% per hour. So this rumor is growing at 5.72% per hour. That's its growth rate. So we're taking a known growth rate and we're just changing the value of time. Okay? Let's look at this next one. A slow leak of gas from a tank is causing the volume of the tank to decrease by 8%. So we have decay. So I know I'm going to do 1 minus 8% is 0.08. Are you guys okay with that? Yes or no? Did I confuse anyone on that? Okay. So what is my decay value? What is my rate? Well, my growth rate is 0.92. That's my B, okay? It says the original volume of gas is 2,600 cubic inches. So we need to write a function for the volume. So 2,600 cubic inches times 0.92, where M is the number of minutes that the gas has been left on. There we go. But what does it happen? This gas leaks, how much is it? Isn't it every 10 minutes? So we have to take our number of minutes and divide it by what? If it's happening every 10 minutes, we're going to divide it by 10. So that's our exponent, m to the 10th. So it says determine the number of minutes to the nearest minute that it takes for the gas to reach half of its volume. Half of its volume. So what is half of 26? So we were looking for a volume that's 1,300. We're looking for a volume that's 1,300. So I'm going to draw us a graph here. So we know that it began at 2,600. I'm going to go halfway in between, and I'm going to put 1,300. And I'm going to draw a horizontal line at 1,300. This is just the line y equals 1,300. Well, we know that it began at 2,600. And we know that if we take, did it give us an ordered pair at all? Okay. So if we figure out this value right here per minute, we could take 0.92 to the 1/10th power times m. Can someone do that and tell me what our value is in there? So we're trying to get rid of the fractional exponent. So what is 0.92 to the 1/10th power? You guys all have a calculator. Someone pick up their calculator. Awake. Awaken your body. Awaken your brain. What'd you get? So 2,600 times point. I can't hear you, Kane. What did you get for that? 0.9996? 9916? Did anybody else get that? Okay. So there we go. Put that into your table. Put that into your table and find out, get yourself some ordered pairs. So I'm going to go to y equals 2,600 parenthesis 0.9916 to the power of x. And I'm going to get a table of values because I'm looking for when x is going to be what? Or my output y is going to be what? 1,300. I want to know how many minutes is it going to take for my output to be 1,300. So when I scroll through my table, I find out that it reaches 1,300 at about 80, in between 82 and 83 minutes, right? So here I go. If I say that this is 83 minutes, this is where my graph intersects this line. Okay? I'm just going to keep on going, just like this. All I'm doing is making a sketch. Does everybody know how to put an equation into their y equals and then look at your table? So all I did was look for the output of 1,300, okay? All right. If H represents the number of hours the gas has leaked, write a function to show how you created your model. Let's see. We're going to skip that. We're going to skip that. By what percent? We already did this. By what percent is the volume of gas decreasing in 1 hour? Skip that one. Let's go on to, what is our, I want to do this Euler activity. Okay.